Alright everybody, welcome to this video on projectile motion. Okay, within this video we're going to talk about the following things. We're going to do a quick review on vectors, talk about what a projectile is, talk about the characteristics of a projectile motion, talk about the horizontal and vertical components of velocity, and talk about the initial velocity components, and do some example problems. Okay. So those will be the things that we will cover in this section. So, first up, we'll do a little vector review. So if you remember, vectors can be both added together and broken up. Okay, so for example, we've got our two vectors here, the black vectors right here. Okay, and so if we have these two black vectors, we can add them together to make this red one. And the way we do that is if we draw a little parallelogram. So do the dotted line represents the parallelogram. Make it sure they're parallel to those other vectors, and then you draw another vector going from the origin of the two together to the opposite end of the parallelogram. And that will be our resultant vector when they add up. Okay, here's another example. We have our vector here. Here's the parallelogram parallel to this vector, connecting from the other vector up to here. Then we have our other vector that we put up here to make a parallelogram to here to go across here. Okay, and lastly, we got this third one where we have the vectors going right and left. Okay, so we have our two vectors, draw the parallelogram there. Make sure you're to scale, so meaning make sure that your parallelogram is the same on both sides. Okay, so make sure the scale, okay, and combine them together to make a parallelogram and go right across. Okay. Also, your vectors can be broken up. So if we have this red vector here, we have our axes, okay, and you draw the dotted line going from the point of the vector to the origins on the graph, and then draw your vectors from those points, making on the axes. Okay, so if we have this vector, we have our two components here, and we have this vector and our two components here. Okay, so now go ahead and practice. Go ahead and try this out. What would the addition of those top three vectors be, and what would be the components of the bottom three vectors be? So go ahead and pause the video and figure out for yourself what they would be. Alright, so what did you find out? Alright, if your vectors look something like this, then I'd say you did a pretty good job. If your vectors are a little bit different than what we got here, maybe you should go back and review over how those vector addition and breaking up vectors work. Okay? Okay, so we're going to be talking about projectiles here, but first off, here's a little question for you. Okay, you see these two balls, a red ball and a yellow ball. Both of these balls are falling, but you notice they follow different paths. Okay, so I want you to identify, take a second, write down on a piece of paper what are the similarities and differences of the paths of the yellow and red balls. Take about, go ahead and pause the video so you can go ahead and write that down. Alright. So if you notice here, the red ball, it falls straight down, but the yellow ball does not. It follows a little curved path here. But the yellow ball, the distance from the starting point of the yellow ball and the red ball remains constantly the same the whole time as they fall. Okay, that's one of the major characteristics of falling objects. Is no matter, they always fall at the same rate when they start at the same position. Okay, so we'll look a little bit at why this is the case here. Okay, so first off, what is a projectile? So a projectile is an object upon which the only force acting on it is gravity. A projectile is any object with which once projected or dropped continues in motion of its own inertia, is influenced only by the downward force of gravity. So a projectile is only influenced by gravity. It has a force exerted upon it, then after that force is gone, the only object force on it is gravity. So take a couple seconds and identify what two projectiles are that you see in everyday life. What are two projectiles? Identify two of them. Okay? Okay, some projectiles that students come up with are, you got a ball. That's one that we've used in class. You let a ball go and drop it. That's a projectile. An apple falling from a tree is a projectile. Or even if you go skydiving, you jumping out of the plane and falling before you open your parachute, so just while you're falling, that you would be a projectile there when you jump out of a plane. Those would be examples of free-falling projectiles. Some other examples could be projectiles that get launched in an arc, like we see here. We've got two different types. A ball being thrown up, so like a basketball being shot, or even a cannonball being shot would be a projectile as well. So, or even a bullet being shot out of a gun. Those would be examples of other examples of projectiles. Okay, so these projectiles have a horizontal and a vertical component. Okay, so remember this projectile has only the force of gravity acting upon it. Okay, and while they have gravity acting upon it, they follow the path of a parabola. So if you look at this picture here, you see how this ball follows this path of parabolas as it bounces up and down. You've probably studied a lot about parabolas in your algebra classes. Okay, but you have that path that the parabola follows. Okay, while the parabolas are following this path, there is no horizontal force acting on the projectile. So because there's no force, there's no horizontal acceleration. So the velocity in the horizontal direction is constant. It doesn't change. So as the projectile moves horizontally, it doesn't increase speed or decrease speed in the horizontal direction. Okay? But, as we know, whenever something falls, what force acts on it? Right, gravity acts on it. So as gravity acts on it, it causes it to increase its speed by 9 meters per second downward. That's why the parabolas that this ball makes continually get smaller and smaller and smaller because gravity pulls down on it. Okay, and it pulls down at that velocity of 9.8 meters per second. Okay, so and one thing we can also realize is that a horizontal motion of a projectile is independent of its vertical motion. Now that's important to realize, so I'd write that down. A horizontal motion of a projectile is independent of its vertical motion, meaning that the motion of a motion of the projectile moving up and down is separate or independent from the motion that goes up, right, and left. So its horizontal motion is separate from its vertical motion, completely separate. And that kind of makes our calculations a lot easier when we calculate things here in the future. Okay, so here's an example of that. Here we have a cannon shooting a cannonball off of a cliff. Okay, so we go ahead and shoot the cannon. And if we were shooting it straight, the red dotted line is where the ball would go if gravity did not act on it. We would just have this horizontal component. But because gravity acts on it, it pulls it down. And it follows this parabolic trajectory. Okay, it just pulls it down a little bit here, more, and more. And we've studied how much it has pulled it down and done calculations with that. Okay, so the gravity causes it to fall below its inertial path, its ideal path that is there. Okay, here's another example of that shows the displacement. Okay, so if going in the horizontal direction, the ball would travel at a constant velocity and not change. So 20 meters, 30, 40 meters, and the green dots show where the ball would be. Okay, and so, but we know that gravity also pulls upon it. So the blue dots show where gravity causes the ball to be. And we see that that distance steadily increases, which again we've studied. So, but if we combined the green displacement plus the blue displacement, so if we were to make arrows here, you'd see that the red dot is where the ball would end up. The green plus the blue gives us the red that's there. And that's the case all the way down the line. The green plus the blue equals the red. That would be the displacement would end it up along that red trajectory. Here's some other examples that we can have that show the projectile motion using a vector diagram. Okay, so here at the top we have a cannon being fired. Okay, so the cannonball shoots off. After 1 second, gravity's pulled down on a little bit, giving it a little bit of velocity downward at 9.8 meters per second. After 2 seconds, it's gone up to 9.6 meters per second. 3 seconds, 29.4 meters per second, and so on and so forth. Each second, gravity pulls down on it more and more. But wait a second, look at the horizontal velocity. The horizontal velocity stays the same the whole time. You see there, it's always 20 meters per second, no matter what. The horizontal velocity never changes. But the vertical velocity, up and down, continually increases because of the pull of gravity. All right, another example down here. We have a person throwing the ball up. And again, we notice that the horizontal velocity stays the same at 12 meters per second the whole time. But we give it initially an upward velocity of 9.6. 1 second later, it's slowed down to 9.8. And another second later, it's stopped moving up in the vertical direction. But gravity is still acting on it. And so the next second, it starts moving down at 9.8 meters per second. And the next second later, it's moving down at negative 19.6 meters per second. And if we add up these vectors, these arrows, we would get the actual path the ball is traveling at that moment right there. Okay, so here's a little check to see how well you understand. So, a child sits upright in a wagon, which is moving to the right at a constant speed as shown. The child extends her hand and throws the apple straight upward from her own point of view, while the wagon continues to travel forward at a constant speed. If air resistance is neglected, will the apple land A, behind the wagon, B, in the wagon, or C, in front of the wagon? So go ahead and pause the video, think about that, and decide what happens. Does the apple land in the wagon, in front of the wagon? Sorry, does it land A, behind the wagon, B, in front of the wagon, or C, in front of the wagon? Pause the video now. Alright, so what answer did you choose? Did you choose B? That's the one that I think is most correct. If you came up with a different answer, go ahead and rewind the video and review over the concepts we just talked about to see if you can figure out why it's supposed to be B. Okay, next question here. A boy on a small hill aims his water balloon slingshot horizontally straight at a second boy hanging from a tree branch at a distance d away. At the instant the water balloon is released, the second boy lets go and falls from the tree, hoping to avoid being hit. Explain that he made the wrong move. So for this, I want you to either go get your parent, a sibling, or a friend, someone that you can talk to right now to explain why the boy made the wrong move. Obviously, he didn't explain physics. He didn't take physics yet, so he didn't know about physics and why this is. And also, ignore air resistance. But go get a friend, pause the video, go get a friend, a parent, or a sibling, and explain to them why that's the case. Alright, hopefully you've made your friend a little bit smarter in physics. So we'll go ahead and move on. Okay, so remember, as we talked about earlier, and I had you write down, the vertical and the horizontal components are separate. They're independent of each other. So when we're doing calculations with projectile motion, we can keep that in mind, and we do our calculations completely independent in both the vertical and the horizontal direction. Okay, so we can see here two sets of equations, but don't freak out. I know they look intense, but these are equations that we've used before. Okay, we have our vertical equations and our horizontal equations. Okay, we distinguish these ones by using the subscripts Vx or Vy. Those x's and the y's tell us whether it's in the vertical direction or in the horizontal direction. Okay, we've got our equation here. Initial velocity or final velocity in the y direction equals initial velocity in the y direction plus acceleration in the y direction times the time. Or and there's that equation. Also for our distance, we got distance in the y direction equals velocity in the initial velocity in the y direction times time plus 1/2 times acceleration in the y direction times the time squared. Okay, it's exactly the same for the horizontal direction. Just those subscripts is what changes. Okay, so that's the only difference between these two equations, is the direction that it's going on. And we've used both of these equations in class many times over the last few days. Okay. One other thing to note, since acceleration in the y direction, acceleration in the x direction is 0, the horizontal equations can be simplified to these two equations. The distance in the x direction is equal to the initial velocity in the x direction times time, and the final velocity in the x direction is equal to the initial velocity in the x direction. Alright, so we've got these equations now. Alright, congratulations, you've now successfully done a video on, or not a video, you've now successfully done a projectile motion problem. Your first one. Great job, pat you on the back. Okay, so now some other side notes, some cool things about projectile motion. The angle that a projectile is launched at matters. So here we've got a graph that shows the vertical displacement, or how high the projectile goes, versus how long the projectile goes when it's launched at a certain angle. So here we've got 15, here's 30s, here's 45, 60, and 75. Okay, so you can see this, that when an object is launched at an angle of 15, you have a very long vertical displacement and a very long horizontal displacement and a very short vertical displacement. Okay, but at 75 you have a very high vertical displacement but a very short horizontal displacement. But what do you notice about both 15 and 75? Right, both of them end at the same point. Both of them go to 10 meters. You get the same resultant, but from different angles. Same thing with 30. 30, you have a longer horizontal component than you do vertical, and then with 60, you have a longer vertical component than you do horizontal. And thereby, when you add those two together, it gives you the same resultant vector, giving you a distance of 17 that it travels. Alright, look at 45. 45 is our longest. Why do you think 45 degrees gives you the best, the longest distance that you can travel? If you said it's because 45 degree has the same vertical displacement as you did horizontal displacement, you're correct, because the velocity in the vertical direction is the same as the velocity in the horizontal direction. That gives you the longest distance possible, to giving you the best angle to fire something. So why does this matter? Why do we care about where something lands versus on an angle? Well, let's look at this this extreme biker here going off this jump. His jump has to be at the right angle, so he's going to land at the right spot. If they put the angle of the jump too shallow, he might overshoot it. If they put it too high, he might undershoot it. So we got to make sure that the angle is just right so he can land at the right spot. Also, if they want the best height possible, that one angle will be a better height than the other. So there's numerous different reasons why that applies. Okay, another thing that matters is air resistance. Okay, we've seen this a little bit before, that air resistance slows things down. Okay, air acts like friction for things moving through it. So when we launch something in a projectile motion, it follows the green path. The green path is the ideal path. However, in real life, when you launch something, it experiences air resistance. So, because of the air resistance, it tends to follow the blue path, causing it to fall a little short. So there's an example of air resistance. Air resistance does play a role and does cause it to be short. That's why when we clarify in most of our problems that ignoring air resistance, what would it be? Alright, last really cool fact. Let's say I build a mountain, and it's a huge mountain that goes all the way up outside the atmosphere, so there's no air resistance. We don't have to worry about air resistance. Okay? If I put a cannon on top of that mountain and launch it out, what's going to happen? Let's say I launch it at 2 kilometers per second. I launch it out at 2 kilometers per second, it's going to launch off. Here's my mountain, here's my cannon. It's going to launch out and land at position A. All right, it's going to hit the Earth. Okay, so let's say I go ahead and I go, okay, I want to see what happens when I launch it even faster. So I launch it at 5 kilometers per second. Okay, so I launch it at a faster speed. Well, it goes ahead and goes and comes down and hits farther away at point B. Then I get a little bit more energy and I go ahead and launch my cannonball at 8 meters per second. Okay, so it launches out at 8 meters per second, and it travels and it travels and it travels and it travels, and it keeps going. It, in fact, never ends up hitting the surface of the Earth. Why is that? Well, it's because gravity is still pulling on it, but it never hits the ground. It so happens that if you launch it at 8 meters per second squared, that the distance it travels forward and then the distance it falls down is equal or less is equal to the curvature of the Earth. So as the object falls, the Earth also falls away with it. But it keeps moving forward with that horizontal component. But it keeps falling at the same time. And that's what we mean by an object experiencing free fall gravity, because it doesn't have, it's experiencing gravity, but it's falling at the same time. And the curvature of the Earth is also falling away from it at the same time, thereby causing it to go into orbit. Well, let's say I go ahead and launch my cannonball even faster. Let's say at 10 kilometers an hour. Well, it's still going to be in an orbit, but it's going to be in an elliptical orbit or an oval, following this path like D, going around the Earth, rather than like a circle like C. And then lastly, what happens if I go ahead and give it a really great speed, like let's say 11.2. If I give it 11.2, that is actually the escape velocity of the Earth. And so if they were to go at speed 11.2, it's going to follow the E path here and just go off and escape the gravity of the Earth, because it's going fast enough that can't be captured by gravity and won't fall back in onto the Earth, and that's what we refer to as escape velocity. So if you want an object to escape the gravity of the Earth, you got to just launch it at a speed of 11.2 kilometers an hour, which, by the way, if you did it in the atmosphere, that would burn it up to a crisp. But if you want it just to be in the orbit of the Earth, you just got to launch it at a speed of 8 kilometers per second, which in miles per hour is about 18,000 miles an hour. So good luck at launching something into orbit. You got to get up outside of the atmosphere so it can do so. So that's our video on projectile motion. Hope you enjoyed it, and good luck on your homework. Hey, so that's the end of the video. The next segment of the video is not required, but it does give you practice problems. So if you want to work on practice problems, you can watch the rest of the video and go through that. Thanks. How do I end that?
Go down so that you can actually see your...
There. Let's go ahead and take an opportunity to use these equations for a calculation. So we've got two problems here, and I'll work through it with you, so don't freak out. Okay, so question number 1, Anna drops a ball from rest at the top of an 80-meter high cliff. How much time will it take for the ball to reach the ground, and at what height will the ball be after each second of motion? Okay, so what is our known? Remember, set up our six step system. So our known, what do we know? Well, we know that the height of the cliff is 80 meters. We also know that the effect of gravity is 10 meters per second per second. We're going to use 10 just to simplify our calculations. Okay? What else do we know? We do know an initial velocity. Initial velocity is because it says it drops the ball from rest. So we know the initial velocity is equal to 0 meters per second. In which direction is that again? Initial velocity in the y direction. Okay, initial velocity in the y direction. Okay, so that's our known. What is our target? So if that's our known, what's our target? Okay, our target is what is the time it takes to reach it, and also know what it wants to know the distance. What is our time, and what's the distance? Okay, but we'll just look first. We'll look at the time. Okay, what's the equation that's going to help us to get to know the time? Okay, we can go ahead and look back at our equations here, and we can use the second one there of our vertical equations. We can use that second one. So that second one is distance in the y direction equals velocity, initial velocity in the y direction times the time, plus 1/2 acceleration in the y direction times the time squared. Okay, so now going back to our problem, we can go ahead, I've got our equation, we can go ahead and calculate our time. Okay, so our distance is 80 meters, is what we want to travel. Okay, our velocity, our initial velocity, remember, is 0. So we can go ahead and put 0 there, plus 1/2 times the acceleration. And our acceleration is in the y direction. It's going in the negative direction, because downward we designate as negative. So that's negative 10 meters per second squared. And then t is what we're solving for. So we get 80 meters equals 1/2 times the time. So 1/2 times 10, that would be 5 times the time squared. And we got 80 divided by 5. Let's divide both sides by 5 to get our total of 16 times the time squared. And we square root both sides, and then we get that is 4 times the time. Okay, so it took 4 seconds for it to drop from that height. Okay, so that's the first half part of the question. The second asks, what is the height of the ball after each second of motion? So we go ahead and use that same equation, but we're trying to figure out what it is at each second. So you can go ahead and plug 1 in for both of those, and 2 into 1, 2, 3, and 3 in for each of those. So when you plug 1 in, we get d equals, our initial velocity is 0, remember, plus 1/2 negative 10 times the 1. And that simplifies out to 5. Alright, and I'll let you go ahead and calculate the rest of those down the line using that equation. Okay, so that's the first one. Now let's look at the second equation here. A cannonball is launched horizontally from the top of an 80-meter high cliff. So we got the same cliff. How much time will it take for the ball to reach the ground? And what height will the ball be after each second of travel? Okay, so what's the question asking for here? It's asking for exactly the same thing. Okay, it's asking for the time that's going to take the travel downward, and also the distance it travels at each second. Okay, and even though we added in this horizontal component here, as you can see here in the picture, the horizontal component is there. Okay, the time vertically is exactly the same. So this problem, the second problem, is exactly the same as the first problem. And you can see there, even though there is that horizontal component, we don't worry about the horizontal component. And they don't even give us what that horizontal velocity is. So it's exactly the same. Okay. Next up, when we do a horizontal component, when there is a horizontal component that we're dealing with, we go ahead and can set it up using a table like this one. Okay, use a table where you organize your data, we've used one of these tables before, where you have your velocity in the x direction, your velocity in the y direction, your acceleration in the x direction, and your acceleration in the y direction. Okay, so let's look at an example with this one. Okay, so we want to go ahead and fill in the table using the indicated values. We have an initial velocity in the x direction of 15, and initial velocity in the y direction of 30. Okay, so let's think about what the acceleration in the x direction is. So when we have a parabolic a projectile, what is the acceleration in the x direction? Right, 0. There is no acceleration in the x direction. So we can go ahead and add in 0 for all of these values. Okay? What is the acceleration in the y direction? What is the only force acting in the y direction? Gravity. Okay? And gravity acts at a force of negative 10 meters per second squared. So you can go ahead and fill in your table that you've made, you fill in this whole table with negative 10 meters per second squared. Okay? So now we can go ahead and look at these. So if our value, remember our velocity changes only by how much our acceleration is. So after 1 second, how much does our velocity in the x direction change? And we're looking over here at our acceleration column, 0. So this one will be 15. All right. Time equals 2. What is it now? Again, it's still 15 because our acceleration in the x direction is also 0. In fact, all of these down the line are going to be 15 because our acceleration in that direction is 0. Okay. Now, how does our velocity change? So we start at 30. After 1 second, what's our acceleration? That's right, 20. We've done a problem like this before. 20. After 2 seconds, what's our velocity? 10. 3 seconds. 0. Okay. And now remember the velocity. Even though the velocity is 0, the acceleration is still there. So the ball is now going to change direction. So what is the time? So at time equals 4, what is the velocity in the y direction? You said negative 10, that's right. And then in 5 seconds, negative 20. And at 6 seconds, it's negative 30. All right, so you should now have your table filled out. Okay, so now let's go ahead and make another table and use it for this next problem. The diagram below shows the trajectory for a projectile launched non-horizontally from an elevated position on top of a cliff. The initial horizontal and vertical components of the velocity are 8 meters per second and 20 meters per second, respectively. So we can see that here, 20 meters, 8 meters. The position of the object at 1 second intervals are shown. Determine the horizontal and vertical velocities at each instance shown in the diagram. Okay, so again, we make a table like this. Our initial velocity here would be 8, and our initial velocity here would be 20. Okay, and so what's our acceleration in the x direction? Again, it's the same, 0. There is no acceleration in the x direction. All right, what's our acceleration in the y direction? Negative 10 meters per second squared. Again, that's caused by gravity. Okay, and then so at time equals 1, what's now going to be our acceleration or our velocity at time equals 1 in the x direction? The hint, what's our acceleration? Because our acceleration is 0, our velocity is not going to change. So it's still going to be 8. And at time equals 2, it's going to be 8. And so on and so forth. Okay? And now, again, looking at our velocity in the y direction, so we start at 20. After 1 second, what's our velocity after 1 second? Is 10. And I'll let you go ahead and finish filling out the graph. So go ahead, the table. So go ahead and pause the video and finish filling out the table for the rest of that.